Okay, let's look beneath the surface. Way, way beneath, deep into geological time, in a part of the world you already know is packed with energy resources. What secrets are still hiding down there, in the ancient rocks, maybe far from where the oil and gas typically flow?
That's exactly what we're exploring today. We're doing a deep dive into a recent scientific paper focused on one specific rock layer, the Ordovician Rayan Shale member in central Saudi Arabia. Think of this paper as our map.
And our mission, to unpack what this research tells us about this particular rock unit, its makeup, how it formed, and the key thing is its potential significance, especially when we think about unconventional hydrocarbons.
Right.
We're basically trying to give you the shortcut to understanding the key findings from this really detailed scientific work.
So let's set the scene a bit. Where does this Rayan Shale actually sit in the grand scheme of geological time and place?
Geologically speaking, it's a pretty significant layer. It's part of the much larger Ordovician Qasim Formation. If you picture the Qasim Formation as this thick stack of ancient sediments, the Ratine Shale member is up towards the top of that stack. It sits right between the Kaffa sandstone below and the Quara Formation above it.
And that's important because the Qasim Formation itself isn't exactly unknown in the energy world, is it?
No, not at all.
The sandstones in there, like the Kaffa and Quara you mentioned, they're already known gas reservoirs in some places. But the shaly parts, like this Rhea member, they haven't really been the main focus for their own potential. Either as source rocks or unconventional reservoirs themselves.
Ah, okay.
And that's what makes this paper so interesting, is taking a really close look at this less explored shale.
All right, let's get into the study then. The researchers zeroed in on a specific location, didn't they?
They did, yeah. They studied a section of the Iraqi shale that's really well exposed right at the surface, an outcrop. This specific spot is at Kashamuran. That's actually where the rock unit gets its name.
Kashamuran, got it.
And the section they looked at was about 16 meters thick.
16 meters, that's quite a bit of ancient seabed turned into rock. So what story did they piece together by looking so closely at all those layers?
Well, they saw several different types of rock layers, or what geologists call lithofacies. Right down at the bottom of the section they studied, they found sandstone, but it was heavily bioturbated.
Bioturbated, meaning?
Signs of life. Ancient organisms burrowing through it, churning up the sediment. But then as they moved up, they hit these laminated shales, really fine layers, like pages in a book. That suggests, calmer conditions when the sediment was settling.
Okay.
And some of these laminated shales only showed partial burrowing, which kind of hints at times when maybe life wasn't so active down there. They also found layers of mudstone and sandstone mixed within the shales. So, bit of variety.
And you mentioned fossils earlier. What kind of snapshots of ancient life did they actually find preserved in there?
Yeah, they found imprints of graptolites. These are fossils of colonial marine animals. They often look like tiny, delicate saw blades in the rock.
Ah, okay.
Finding graptolites is actually a really useful clue about the specific marine environment back then. And they even found tiny fish scale remains. Little bits and pieces, but they tell you life was there.
That definitely helps paint a picture. But what about the rock itself, like the basic building blocks? What's it actually made of?
Good question. So to figure that out, they used some pretty standard but powerful lab techniques. Things like X-ray diffraction or XRD that tells you the specific minerals present. And also QEM-scan, which is it's the fancy microscopy method that maps out minerals and textures really precisely.
And what did those tests show?
The main things were clay minerals, kaolinite, chlorite, elite, along with quartz, feldspars, some carbonate minerals, and mica. They also picked up smaller amounts of other stuff like gypsum, anhydrite, and pyrite.
So, a mix, but heavy on the clays and quartz-like minerals. Did that lead them to classify the rock types more specifically than just shale?
Yes, exactly. Based on how much of each mineral group was there, they sorted the rocks from the outcrop into three main types: silica-rich argillaceous mudstone, clay-rich silicious mudstone, and mixed silicious mudstone.
All right.
It sounds a bit technical, but it's basically describing the balance between the clay content, that's the argillaceous part, and the silica, like quartz, the silicious part. It's a much more detailed picture.
Okay, so now they know what the layers look like, the fossils, the minerals. How did they put all that together to figure out what the world was like when this Rayan Shale was being deposited millions of years ago?
Well, all those pieces, the rock types, the structures like laminations and burrows, the minerals, they all act like clues. Put them together, and they strongly point towards the Rayan Shale outcrop being laid down in a shallow marine environment. A shallow sea.
Shallow seas. That fits with what we know about this region back in the Ordovician period. What about the conditions in that sea? Like oxygen levels. You said the laminations and graptolites were important clues there.
Absolutely key. Those fine, undisturbed layers, the laminations, and fossils like graptolites, they strongly suggest periods where the bottom waters didn't have much dissolved oxygen.
Okay.
We call those conditions anoxic, or maybe even euxinic, which means they might have had hydrogen sulfide present. And that low oxygen state is really important because it helps preserve organic matter.
Right. The stuff that could eventually become oil or gas.
Exactly.
Yeah.
But it wasn't always like that. The fact that they also found layers with burrows tells a different story.
Ah, the bioturbation again.
Yeah, that means there were also times when oxygen levels improved enough for burrowing creatures to live and thrive. So it wasn't just a stagnant pool. It was a shallow sea with, let's say, fluctuating oxygen conditions.
A sea with different moods,
Yeah.
switching between oxygen-starved and more breathable for bottom dwellers. Did they use chemistry to back this up?
They did. They used X-ray fluorescence, or XRF, to measure the overall elemental composition of the rocks. And by looking at the ratios of certain elements, ones that act like proxies because they're sensitive to oxygen levels.
Like what?
Things like the relationship between aluminum oxide and vanadium, or nickel and vanadium. These geochemical signals gave strong support to that interpretation. Mostly shallow marine, but with periods of low oxygen, anoxic to euxinic conditions.
Okay, so they've established an environment that, at least sometimes, sounds pretty good for preserving the raw materials for hydrocarbons. But the paper really flags a big issue with these surface samples: weathering.
Yes, this is super important, and it's a common challenge when you study rocks exposed at the surface, these outcrops. They calculated something called the chemical index of weathering, or
Right.
CIW.
CIW, okay.
It basically measures how much chemical alteration the rock has suffered since it got exposed to air and water. And the results showed these Rehanian outcrop samples have been hit hard by chemical weathering.
And the consequence.
The conclusion was pretty stark. This weathering has significantly degraded, basically damaged or destroyed, a lot of the original organic matter that might have been in these rocks when they were first deposited.
Ah, so the exposure at the surface kind of erased or broke down the organic richness that might have been there to begin with. That makes total sense. Okay, what else did they find when they zoomed in even closer down to the microscopic scale?
Right. So using those techniques like QIMscan and scanning electron microscopy, the SEM, along with elemental analysis, that lets you see the rock's texture in incredible detail. And crucially, you can see the tiny spaces within it, the pore system.
The pores, right, where fluids, water, oil, gas could potentially hang out.
Exactly. And they found different kinds of pores in these samples. There were intraparticle pores, tiny spaces inside mineral grains or bits of fossils. They also saw dissolution pores. Yeah, like where certain minerals, maybe feldspar, had partly dissolved away over time, leaving these little gaps or voids. And they saw fracture pores, two small, crack-like spaces, often along mica flakes where grains press together. So yes, the spaces are there. Potential storage exists.
Okay, the spaces exist, but rocks don't just sit there after they're buried. They change, right? That process called diagenesis. What did the microscope show about those changes?
It showed quite a lot, actually, and much of it wasn't great news for fluid flow. They saw significant diagenesis. A big one was cementation.
Like minerals filling up the gaps?
Precisely. New minerals, especially dolomite and kaolinite in this case, had crystallized within the pore spaces, basically plugging them up, reducing the open room. They also saw clay minerals kind of blocking the connections between the pore throats, and clear signs of compaction, where grains were squeezed really tightly together.
And I'm guessing that cement, the blocked pathways, the compaction, that makes it harder for fluids like hydrocarbons to move through or be stored.
You got it. That's the key insight here. These specific diagenetic changes they saw in the outcrop samples, they're major roadblocks. They significantly cut down both the porosity, the total amount of space, and, maybe even more importantly, the permeability.
Permeability being how easily fluids can flow through.
Right. So all this makes the rock, at least in this outcrop state, much less likely to be an effective reservoir rock or a good target for unconventional extraction methods like fracking.
Okay, that makes sense. So let's get to the heart of the energy potential question, the organic matter itself. What did the specific organic geochemistry tests show about, the stuff that could actually turn into hydrocarbons?
For that, they used rock-evil pyrolysis. It's a standard lab technique where you heat the rock samples in a controlled way. It tells you how much organic carbon is there, what type it is, and how mature it is.
Mature meaning like how cooked it's been by geological heat.
Exactly. Has it been heated enough over millions of years to actually generate oil or gas from the original organic stuff?
And for these specific samples, the ones from the outcrop at Kashryan, what was the verdict?
Well, the findings from these surface samples were, let's say, revealing, but maybe not super encouraging for finding unconventional potential right there at the surface. They found generally low total organic carbon TOC values, mostly less than 1%.
Okay, not very rich.
No. And the type of organic matter, the kerogen, was mostly type 3 and some mixed type 3, which, by standard classifications, suggests only poor to fair potential for generating hydrocarbons in these specific samples.
And the maturity, how cooked was it?
They looked at indicators like Tmax and the production index, or PI. And those numbers pretty clearly show that the organic matter in these outcrop samples is generally immature.
Immature, so not heated enough.
Right. It just hasn't been buried deep enough for long enough to reach the temperatures needed to generate significant amounts of oil or gas.
So low amount of organic stuff, and what is there hasn't matured. But that feels a bit odd because you said earlier the environment sometimes had low oxygen, which usually helps preserve organic matter, right?
Exactly. And this is where the study really highlights the critical difference between what you see at the surface and what might be going on deeper down.
Okay.
The researchers believe that even though the original depositional environment was likely pretty good for preserving organics sometimes, two big things worked against these specific outcrop samples. First, as we talked about, that intense chemical weathering at the surface would have just destroyed a lot of it.
Right, the weathering effect.
And second, they think there was early tectonic uplift in this particular area, relatively soon after the sediments were laid down. This uplift would have brought the rock closer to the surface much earlier, exposing it to that weathering and stopping it from getting buried deeply enough to cook properly, to reach thermal maturity.
Okay. So uplift stopped the cooking process and exposed it to degradation.
Yeah. They even mentioned similar weathering effects messing with TOC, results in outcrop samples of another important Saudi shale, the Qasaiba Formation.
So the really crucial insight here is that this surface outcrop, while useful for studying the rock type and how it formed, might actually be giving us a misleading picture of the Ramo member's potential deeper underground elsewhere.
That's exactly it. That's a key takeaway. The paper actually mentions reports, internal Saudi Aramco reports. It seems suggesting that samples of the Ramo member taken from the subsurface, from wells, are organic rich.
Oh, interesting.
Yeah. It strongly implies that if you get away from this specific outcrop location, with its history of weathering and early uplift, the RAFO member buried deep down could be a very different story, potentially a much more promising story for hydrocarbon source potential.
That difference between surface and subsurface is really critical then. Was there any hint of hydrocarbon activity at all in these outcrop samples, maybe something migrating in from somewhere else?
Yes. Actually, there was one little intriguing bit of data. One sample stood out on their maturity plots. It had a higher production index than you'd expect for immature organic matter.
Meaning?
It suggests the presence of hydrocarbons that weren't generated in that rock, but migrated into it from somewhere else. Mobile hydrocarbons. The researchers speculate these probably came up from the underlying Hanadir Shale unit, which is deeper and known to be an organic-rich source rock in this region.
So a little sign of plumbing, potentially?
Kind of, yeah. A small clue, but it hints at connections and possible hydrocarbon movement deeper down.
Okay, let's try and pull this all together. Why does spending all this effort diving deep into one, 16-meter slice of ancient rock actually matter to you listening right now?
Yeah, what are the big takeaways from this deep dive into the Russian shale outcrop?
Well, first, it shows us that at the surface, this Russian shale tells a story of a shallow sea with oxygen levels that went up and down. It's made of a mix of clays and silica, forming these different mudstone types.
Right. And it does have pore space, potential storage, but that potential, at least here, is seriously damaged by cementation and compaction that happened after deposition.
And crucially, the organic matter in these specific surface samples is low. It's immature, and it's poorly preserved. But that's likely because of what happened later, the weathering and uplift at this spot, not necessarily because the original environment was bad.
Exactly. So studying the surface is vital for understanding the rock's basic character and depositional setting. but it also screams caution about extrapolating directly to subsurface potential, especially in areas with complex geological histories.
It really underscores the need for this kind of detailed work.
Absolutely.
Yeah.
This research is a really valuable piece in the bigger puzzle of evaluating unconventional hydrocarbon potential in Saudi Arabia's older Paleozoic rocks. These are a huge frontier beyond the supergiant conventional fields the kingdom is famous for.
Hmm.
And it just highlights how essential these detailed, multi-pronged analyses are. Combining what you see in the field with microscopy, mineralogy, geochemistry. It's the only way to really get under the hood and assess a rock unit's true potential, revealing things like specific cement types or the impact of weathering that you'd otherwise miss.
Yeah, this deep dive into the routine shale outcrop really shows how even, seemingly subtle details locked away in ancient rocks can tell such a complex story about past worlds, geological twists and turns, and maybe, just maybe, resources hidden deep underground.
It certainly does. And it leaves us with a pretty big question, doesn't it? Given that stark difference between this weathered, immature outcrop and the hints of organic-rich routine shale down below, what are the truly critical geological factors? What makes those sweet spots for unconventional hydrocarbons in ancient shales? How do we find them when the clues we see right at the surface can actually point us in the wrong direction?